Hi, everyone. I'm Doug Black, editor-in-chief at insideHPC. And today, as part of our series of interviews on behalf of HPC industry analyst firm Hyperion Research, we're talking with Rick Stevens of Argonne National Laboratory, where he's Associate Lab Director and Argonne Distinguished Fellow. So, Rick, welcome.
Thanks, Doug. Glad to be here.
Okay, thanks. Rick gave a really interesting talk at a Hyperion event in Washington not long ago. Much of it was a look ahead at the Department of Energy's next generation supercomputing strategy, part of which is referred to, part of it could be the Integrated Research Infrastructure, the IRI, and also how post-exascale supercomputing will incorporate AI for science, quantum computing, and also how to deal with really massive power consumption challenges as we move up in supercomputing power. So, Rick, if you would, please go through some of the highlights from that presentation.
Well, I think I talked about three or four big topics, these kind of themes that we're working on as part of our post-exascale strategy. One of them you already mentioned, which is IRI. This is the idea of the Integrated Research Infrastructure concept. This is probably best thought of as a way of building out the connectivity that integrates computing and networking and experimental facilities into a coherent kind of problem-solving environment for the Department of Energy community and the academics that are supported by that, by those programs. And that would include distributed computing. It would include data streaming. It would include, AI at the edge. It includes a lot of, edge to center integration, and so on. So that's one element of the strategy, and that brings in a lot of the experimentalists and the experimental facilities into a coherent computing structure. And we need to do that because over the years, of course, there's lots of computing associated with different experimental facilities, but there's no coherent software architecture or services architecture that allows somebody to write applications that can kind of support that whole community in a coherent way. So that's one part of it. Another part of it is the AI for science direction. So as your listeners know or watchers know, that over the last couple of years, there's been a series of town hall meetings around the topics of AI for science, and more recently for science, energy, and national security, that have been organized by the labs, and have a lot of people participated. And there's just huge opportunity there for building forms of AI that are integrated with scientific needs, whether it's language models that can ingest scientific papers and scientific data sets to help us in knowledge distillation and knowledge integration, or whether it's systems that can help us write and optimize scientific codes, or that can predict properties of materials, or that combine robots and AI to help us accelerate experimental science and control large facilities like fusion reactors. So there's many opportunities on the AI for science side, and DOE is already investing a lot in AI, and we think that there could be even more progress made if there was a program that kind of followed the exascale in that direction. Of course, quantum is a huge topic in the country and in DOE. There's the National Quantum Initiative and the Quantum Information Science Centers that DOE stood up a few years ago. I think the big opportunity, and it's a long-range opportunity, is for DOE to work out how to be a partner with the leading quantum technology developers to stand up a handful of quantum computers at scale, not these kind of 100 to 1,000 qubit machines, but machines that are kind of 100,000 qubits or 1,000,000 qubits that, with the right error correction schemes, could be actually used on real problems where the value of what we can do on the quantum computer exceeds the cost of building that computer. So that's the quantum front, and that's a long-term opportunity. It's probably 10 to 20 years out. A lot of progress will need to be made, where there's still a lot of open questions about how to build reliable qubits, build systems that have thousands of virtual reliable qubits, maybe sitting on top of 1,000,000 unreliable qubits or more, with a lot of quantum error correction and ancillary kind of services, and of course the whole software stack. And a quantum computer at those scales will be fully integrated with classical machines at scale at that time as well, because every quantum program is really a hybrid computation. So there's a need to really design architectures that tightly couple with quantum accelerators as they become available. And then finally, we have to keep making progress on the foundational classical systems on which everything currently depends. And this would be best categorized as something like a zeta scale initiative, something that looks vaguely familiar to what we did with exascale, that is pushing on future systems, trying to target another factor of 1,000 in kind of overall performance. Might be easier to do that for AI applications, AI data types, sooner, because they can use less precision, so forth. But zeta scale has a huge set of challenges in terms of reliability, in terms of power, in terms of scalability, and so forth. So a lot to do actually over the next couple of decades.
Yeah, now let's take in contexts relatively short term zeta scale, as opposed some of the other longer term problems. The power consumption alone is really quite staggering. We saw Lisa Su and others have made a comment that possibly supercomputers of the future of the 2030s will need their own nuclear power plants.
Well, that's a common refrain when people start adding up the total power based on a current, power consumption. I mean, if the target for exascale was to hit kind of a peak exaflop at around 20 megawatts, and the systems at Oak Ridge and Argonne are in that ballpark. But to get to a zeta scale, right, if you just linearly scaled it up, you'd be at 20 gigawatts, which is per zetaflop, which is not just one power plant, but like 20 nuclear power plants or something like that. So that's not going to happen. It would be like, huge amounts of capacity just for one computer. So that's not going to happen. It's just not really feasible to do it. So the question is, how close can we get to another factor of say 1,000 improvement in power efficiency? And that's where I think we don't really have an idea of how to get that, that progress that we would need. Maybe we can get factors of 10, factors of 100, but getting a factor of 1,000 is going to require a lot of invention, and maybe different computing models, different substrates, and so forth. And that's not going to happen fast. I think, with the slowdown in equivalent of Moore's law on scaling, and actually also kind of the increase in AI as a driver for architecture, the push to have say 10 to the 21 operations per second in 64-bit is going to be less than the push to achieve that similar kind of rate for, say, low precision, FP8 or FP16 kinds of precisions, where current, AI, large-scale AI systems could use that, kind of right away. So I think we'll see these machines take a while. My guess is it won't happen before 35, and maybe even after that. It's just a lot of progress would have to happen.
Rick, talk to us a little bit about AI for science. I mean, that's such an important theme, and maybe for people who aren't overly familiar with the idea. But part of the implications of AI for science is moving simulations into this area, sort of data-driven models, where you could get a tremendous acceleration.
Yeah, so one of the fascinating things that's been going on in the last 5 or 6 years has been the exploration of automatically trained or learned surrogate models. So these are sometimes called ML surrogates or AI surrogates, but the idea is that you take a simulation code, a climate code or a density functional code or something, and you run it on a number of scenarios, and you capture the input-output relationships of the model to the kernels, and then you train AI models, ML models, to essentially replicate that behavior of the computational kernel. And then in inference mode, for future simulations, you run this ML kernel instead of the traditional PDE or integrator that you have. And when you do that, often you can get similar accuracy and many orders of magnitude speed up. And there's many papers on this, many different applications that this has been demonstrated on, and including some stuff we've done where we've used deep learning models to essentially act as surrogates for small molecule drug docking, physics-based codes, and we get speed ups of up to 10 million, 20 million sometimes. So if you just assume that for many applications, you might be able to get a factor of 1,000. That means even on exascale hardware, you might be able to run effectively at zeta scale performance. So that's super exciting. In climate, there's been even more work done, and this is in other areas too, where instead of just replacing a kernel but keeping kind of the rest of the infrastructure the same, would be to move more towards models that are trained end to end to predict the thing that you're ultimately interested in. So in the context of, say, weather or climate, it would be trying to go from initial conditions to the forecast in a direct shot, right? You're not trying to use the ML necessarily to integrate through time. You're just trying to build an approximate model that projects kind of the current state to the final state. And those kinds of models are starting to show some promise. So they're quite interesting. So I think this whole idea of what it means to simulate something and the role that AI or machine learning can play, either as part of it or integrated part of it, or as a replacement for it, or maybe as a wrapper that's managing simulations and so forth. So there's lots of different ways in which AI can be incorporated in simulations. Another one is where the simulation is actually being used primarily as building training data for the models. So this is, of course, already happening in scenarios like self-driving cars and robotic surgery and so on, where you need data sets to train the model, and you need data in particular parts of the distribution that maybe, say, in cars, accident scenarios or rare events, and you just can't get enough of that data by, say, reading all the cameras on cars. You actually want to generate it specifically to cover those cases, and so that's where simulation is being used as the data generator for AI. So I think it's all these things are possible, and they're all at some level happening. I think our idea of AI for science is really trying to build a discipline around all the different ways in which AI can be incorporated into scientific computing, and not just taking off the shelf AI methods and using them, but really understanding what new types of AI do we need to build specifically motivated by the needs of scientific applications.
Okay, great. And, it's interesting. Each of the major throughput milestones, petascale, exascale, the gap between achieving each one seems to be getting longer. I was interested, you were saying maybe mid-2030s will be at zetascale. We've heard sooner estimates, but
it took 12 years to go from peta to exascale. And what's happened recently, of course, is people are measuring the AI performance on hardware and claiming, AI exaflops or something, right? So by 2030, you can certainly achieve something that could do kind of the 21 AI operations. But whether everybody's happy with the idea of renormalizing our definition of an exaflop or zeta scale machine, or any kind of X flop machine, to be normalized to some low precision value, right? I mean, I can build an int4 machine that could do it, probably in 3 or 4 years from now. But is that really what we're trying to do, right?
Right. A useful practical machine.
Well, they could be useful for something. It's just that they're, we tend to think of the current progression of tera to peta to exa and so on as being measured by something like LinPack. And while you could do a mixed precision, we could change the LinPack benchmark such that mixed precision is allowed, and you'll get some speed up from low precision. But if we're just going to say anything that runs in low precision at some rate is the measure, right? Then, I mean, by that measure, the current exascale machines are kind of 20 exaop machines or more, right? Mm-hmm. And that's not how we're talking about them, right? We talk about them as 1 or 2 or something like that, but we're not talking about them as 10 or 20, or if we did int 8 performance, how fast could we do something. So I think when we have to normalize it, right? I mean, the definition that most people would use in terms of a program would be an FP64 based zeta scale machine, and I haven't had nobody propose that happening within 10 years.
Okay. But let's look ahead maybe to 2040, when some of these technologies that will contribute to leadership supercomputing in that time frame, some of these technology, as of now, they always seem to be 10 years away. But let's say it's 2040. Do you sort of have a vision, not only of what the infrastructure would look like, but also the kinds of workloads that could be tackled?
Well, I think it's easier to envision the infrastructure than the workloads, partly because in the software side, the application space and the software space, things move much faster than on the hardware space at some level. I mean, so by 2040, right, that's not quite 20 years from now. We could have million qubit quantum computers that would yield maybe 1,000 reliable qubits, and at that scale we can factor RSA primes, we can solve big quantum chemistry problems, we can, I'm sure, do a few more things that are interesting. Zeta scale hardware, at real FP64 kinds of stuff, which means that for AI you might be pushing towards a YADA op in that time frame. Depending on how we tweak the architectures. So that could be possible. These are probably going to be 100 megawatt. I mean, for the classical machines, they're probably going to be around 100 megawatts, maybe a bit more. The quantum computer is going to be nestled inside some giant zeta scale machine, because that's what it will take to keep it fed. So that's the kind of infrastructure that I see happening. And I see that it might be the case that some of the development paths are so expensive that we are forming big, multinational consortia to do it. There's groups in China, or not China, but well, China will probably try to do it. But I mean, between Japan and the U.S. and Europe, I mean, there's various partnerships that could happen that would allow us to, make headway in some kind of international context. I think on the application side, we're seeing this incredible progress in AI, and that's going to continue, probably. We are going to run out of data at some point. There's already speculation that, at least for language models, that we're on the verge of running out of data, which means that for those models, or for models to improve beyond the capability that we're seeing in things like ChatGPT and so forth, that we'll have to start digging deeper into the idea space of real AI, as opposed to just piggybacking on these generative models that have a relatively simple structure, actually. I mean, the niceties of something like ChatGPT comes from the post-processing of what's coming out of it, and the reinforcement learning and the human factors wrappers that are on it. But the underlying engine is pretty straightforward. It just has a huge amount of training data for it. But we're going to have to go past that. And I think for science, there's a lot of data that we don't yet incorporate into models. In fact, the vast majority of experimental data is never really looked at. So that's an opportunity. But in terms of how the landscape's going to evolve, I think there's a lot of wild cards. There's a national proposal for this thing called the National AI Research Resource. That was an idea to kind of democratize AI by standing up some big resources and making them available to the academic community, particularly for AI research. I think that's an important thing to do if we can do it, because that will get a lot more ideas into at the scale at which people can try experiments that are hard to do now in universities. Of course, you're going to have the tech giants continuing to, in some friendly competition, try to best each other in terms of cool new capabilities, and that's hopefully going to benefit everybody. We need to close the loop on the scientific coupling to these things so that we have models that are actually useful for solving the big scientific and technical questions that the community is trying to work on. So I think it's a hugely exciting time. There's just so much happening, and it's building all on the work of the community of the last 30, 40 years. So it's like almost everything that's been invested in is turning out to be useful, which is kind of interesting.
Yeah, it's amazing. So standing on the shoulders of already pretty significant achievement.
Yeah.
Okay, so looking at the immediate term, Rick, can you give us an update on how the Aurora installation is going?
Yeah, it's going quite well. We're continuing to install node blades. I think the machine should be more or less fully constructed sometime in April. And then, as everybody knows how these things go, we have to stabilize the machine. We have to get through all the functionality and stability tests, the acceptance tests, and make it available, to the broader research community. That'll happen sometime at the end of the year or early next year. I think we have over 180 developers on the Aurora test and development system, which is a 2-rack implementation of Aurora that's been up since November. So there's been a lot of development going on there. I didn't travel anywhere over Christmas and spent 2 weeks blissfully hacking on the machine myself. I was the biggest user during that 2-week time period, which is kind of fun. And we're thinking about some cool things we can do early on with the machine as it's getting stabilized that would be very useful to the community. So those are some things to stay tuned for, some activities that we're doing. But there's early science applications and there's ECP applications, and those will be the first groups to get on the machine. And we'll have users on the machine as soon as the machine is fully deployed, even before we accept it, because we're trying to maximize the opportunity for all the investment that's been done for ECP to have test shots on the machine. So it's very exciting. It's very colorful too when you come look at the machine.
Okay, awesome. Great to hear an encouraging update on that. And we're looking at that to be a 2 exaflop system. Is that correct?
Well, the peak is even higher than that. We'll see what benchmarks we end up running on it. But yeah, it's a substantial machine.
All right, very good. Thanks so much. We've been with Rick Stevens of Argonne National Lab. It's been a pleasure to be with you.